All right, the next type of application we're going to be looking at are regression equations based upon a set of data. We're going to look specifically at exponential regression, although the same thing could be done for logarithmic data. And so what we're going to do here, we have an example where a certain employer offers a $500,000 life insurance policy. The monthly rates are shown for various ages. So for a 32-year-old employee, they're paying $15 a month for this $50,000 life insurance policy and so forth. Here I want to plot a scatter diagram using a graphing utility. So we're going to go to our graphing calculator and we're going to go to the Stat button and we're going to type in all of this data into the graphing utility. So under list 1 and list 2, I want to type in all of that information. Okay, so 32, I'll just kind of go down the list. The list 1 is going to be the age, and it's roughly every 5 years, or exactly every 5 years. And then in list 2, we'll put the rate, the monthly rate, in dollars. Oops. Oh, that's not 46.5, that's just 46. Let's see, 75.5, 118, 195.5, and 326.6. All right, so hopefully I got that all entered correctly. Close enough. All right, so we want to get the scatter diagram in here, so we're going to go to the stat plot, second, and then stat plot, and then we make sure that our plot 1 is on, make sure that we have a scatter diagram selected, list 1 and list 2, and we're going to use a little box for our point. Then I'm going to go to zoom, and I want to go down to the 9th option, which is zoom stat, and that will give me a window that represents that data very well. You can see that there's a curve, it's sort of a gradual increase followed by a much steeper increase towards the end. The second question I have here is what type of function best models the data? It definitely appears that an exponential growth would work for this. A quick way to verify exponential growth even without using the scatter diagram is right off of the data to begin with. If you have a consistent increase in the x variable or the independent variable, then you can use a common ratio in the dependent variable to represent exponential growth or decay. In other words, if you take any data point and divide it by the prior data point, you should get a roughly constant ratio. I'll just demonstrate that here with this set of data just to make sure you can see that it's close anyway. So if I did 18.5 divided by the prior value of 15, I get about 1.23. If I did 26 I guess just 26 divided by 18.5, that's about 1.4, so it's close, it's a little bit off. If I did 46 divided by 26, again I'm taking a data point and dividing by the prior one, that's about 1.8 almost. If I did 75.5 and divided that by the 46, all right, that's getting closer, it's 1.6. 118 divided by 75.5 is around 1.6 again. And you can see that these data points are, the ratios are getting much more consistent as we go. That's about 1.6, 1.7, somewhere in there. And the last ratio, 326.6 divided by 195.5, is again around 1.6, 1.7, somewhere in there. So, so it's getting to be a pretty consistent ratio from one point to the next. Again, that works for exponential data or nearly exponential data as long as you have a consistent increase in the age, right? It's every 5 years. If it wasn't every 5 years, then that ratio wouldn't be consistent. All right, so that verifies that we have a fairly exponential set of data. Part C says build a regression model using a graphing utility. So what we'll do now is we're going to go to Stat, over to Calculate, and I want to build an exponential model since that is what we determined would work. We can, if you notice, we can do natural log regression. That's not what we're doing here. We're going to do exponential regression. And there are many other types of regression, but we're going to focus in on the exponential. And so we hit that. List 1, list 2 is good. I do want to store this. Some of you will have a little different screen here, and you may have to do some other work to get this to store, but I want to store this in my y1 equation so that I can show the graph with the scatter diagram. And so to do that, I'm going to go to my variables button, and I want to store it under y1. So I go over to the y variables, then function, then y1, and then I go down to calculate, and it gives me this. So this equation, y equals a times b to the x, that is going to be the exponential model with an a value of 0.66 and a b value of 1.0957 roughly. Okay. This base, the b value here, being greater than 1 represents the increase, the yearly increase. And so my regression model is going to be y equals 0.66019. Maybe I'll just use 5 places after the decimal. Then I have a base, which is 1.0957 raised to the x power. Again, y is going to be my rate, x is going to be the age. Okay, and so that model does represent the data pretty well, and we can show that. Go to my y equals, it's already typed in for me because I copied it there. If I hit graph, you'll see the exponential model, regression model. That's pretty good. That is very good for the data. Okay. Then it wants me to express the function from part C in the form of this exponential growth model that we saw in some previous examples with population growth using E as its base. So here I have 1.09570 as my base. And so what I really want to do is convert the previous base to the E to the K. So all I have to do, I'll do this down below, is take E to the K, set it equal to 1.09570, and solve for K. So I take the natural log, or convert it to a natural log, right? The natural log of the other side is equal to the argument, or the exponent. So K is equal to the natural log of 1.09570. You could also think of it as taking the natural log of both sides and it canceling with the E on the left. Then I just calculate that natural log. I can go over to my calculator here. Natural log of 1.09570. Oh, I didn't put my parenthesis on there, but I actually don't think that it matters. Oops. Well, let's just make sure. And it doesn't. Okay. And so I get 0.09139 as my K value. 0.091393. Now, 1, 2, 3, 4, 5. I would be consistent. We'll just go 5 places after the decimal there. All right. So in that form, I have n of t equals Now the n sub 0 we don't really have. Well, I guess we do. It's going to be this starting point. That would be at age 0, right? With the rate at age 0. So 0.66019 times, I don't need the parentheses, that's okay, e to the kt. K being this value now, 0.09139 times t. All right, and that's my new exponential model using e as a base rather than the base given in the calculator. Then it says, what would be the monthly rate for a 27-year-old? Well, you go on the list here, right? 27 is not on the list, so we don't actually know that. So we can use that model though. If we go to our the calculate menu, hit second and then calculate, go to value, and we can type in 27 to the model. Now we have a problem here because I have an invalid entry, and that's because my window, my window doesn't actually show 27 on it. I need the window to include 27. So let me just adjust that, make it 25 maybe. And then hit graph, and that just extends this a little bit further left so I have 27 in there. And then once it's done, I go second calculate again. And I can go to value 27, and it gives me 7.7874414. All right, so the monthly rate, I guess I round that to the nearest penny, right? So it's 7.79, $7.79 per month. And that again would be for a 27-year-old. That's how much a 27-year-old would pay per month in order to get this $500,000 life insurance policy.